Hello everyone. In this lecture, we are going to discuss the central limit theorem. Okay, central limit theorem is the most important results in probability theory and statistics. Let's have a look at if we have this is our population. So in the population, we will have, for example, the population is normally distributed with mu and sigma square. Okay, now if we take a representative sample, this is a sample. So sample is a representative subset of the population. Let me change the size a little bit. Okay. Then the sample mean. So sample mean is, this is the population mean. Population variance. This is mu and sigma square. And sample mean, x bar, and variance is s squared. Notice the difference, and we are using different notations to represent the population mean and the sample mean. Now, if we draw samples randomly from the population, then what we have is, for example, we have the first sample, we have maybe first set of sample x11, x12 to x1n, and this is our first sample from the population. Then we will have x1 bar, and then let's get the second sample. Okay, this is x2 bar, and you can get more, and suppose you have xm1, xm2, xmn. Now here we get a total of m samples out. For each sample, we are going to have the sample mean. Now, central limit theorem is to answer the question, if x is normally distributed with mu sigma square, then what is the distribution of x bar? Okay, so central limit theorem, CLT. The fundamental idea is the sum or average of a large number of random variables is approximately normal. That means if we take this random variable and we just take a lot of samples, and then the sample mean is also approximately normal. Okay, now let's derive, because if it is normal, then what is the mean of x bar? What is the variance of x bar? We know the mean of x is mu, variance of x is sigma squared. Now, what is the mean and the variance of x bar? Let's have a look at expectation of x bar, which equals to expectation x1 plus x2. You add all of them together and then divide by n. So this will equals to expectation x1 plus expectation x2, then add all of them together xn divided by n. We know that expectation x1, they are all mu, right? So this will equals to n mu divided by n. So the mean of x bar, or the expectation of x bar, is still mu. Now let's have a look at variance of x bar. This will equals to variance. Also, we add all of them together and then divide by n. Now each x1, x2, xn, they are random variable. Variance x2 and variance xn. But we take this constant over here, 1 over n. We take that out. That is actually, if we want to take that out of the variance sign, this variance sign, we have to do the square. And this will equals to n sigma square divided by n square equals to sigma square over n. Okay, why this one becomes n squared? Because variance, if you add a constant to a random variable, then this will equals to c squared variance x. So now we know this is a central limit theorem. If we have x that is normally distributed with mu and the sigma square, okay? Now, if we know this, central limit theorem tells us x bar is normally distributed with mu and the sigma square over n. In other words, here we didn't take the average, right? If you take the average, you don't change really the mean, but you actually decrease the variation. Okay, that will become sigma square over n. In other words, this is called the mean of x equals to mu sigma x square equals to sigma square. So this is expectation of x, variance of x, and the expectation of x bar equals to mu x bar equals to mu, and the variance of x bar equals to variance of x bar equals to sigma square over n. So make sure you are clear about the notation differences. Now, there are some remarks about the central limit theorem. Let's have a look at those remarks first. The x, so you see we have x1, x2 to xn, right? So it doesn't matter what the distribution is. It follows a particular distribution, right? It doesn't matter what the distribution is. It could be normal. It could be uniform. It could be binomial. Or it could be exponential. Or any other distribution. As long as you add all of them together and then divide by n, it will be approximately normal. So this is the first remark. Second, if the sample size n greater than or equals to 30, the normal approximation of sample mean will be satisfactory. Regardless of the population shape or distribution. Okay, so in the example, we actually assume X follows the normal distribution. Then we take the average, then it is still a normal distribution. But here, what we want to say is, if X is not normally distributed, like a uniform distributed, if you take the sum of a bunch of uniform random variable, it's still approximately normally distributed. If n is greater than or equals to 30, then this will be satisfactory regardless of the population. So if n is less than 30, the CLT will work only if the population, that means the X distribution, is not severely non-normal. That means if the population distribution or the shape, the distribution shape is close to normal distribution, then it will work. However, if n greater than or equals to 30, then no matter what kind of distribution, regardless of the population distribution, if you take the average, the sample mean normal approximation will be satisfactory. Okay. Now, what is a normalization? We know that this is a standard normal distribution. What is a standard normal distribution? Standard normal distribution is represented by Z, that is mean 0, standard deviation 1. Okay. Now, how to do the normalization? Or standardization? So if you have X that is normally distributed with mu and the sigma square, and you can do two things, and you have X bar, normal distribution, sigma square over n. So from here to here, this is a central limit theorem. But if you want to do the standardization, then how do you do that? Okay, then this will be Z equals to X minus mu over sigma. And this will become Z equals to X bar minus mu divided by sigma over square root of n. So this step is called normalization or standardization. How to make it become the become a standard normal distribution. Now, let's have an example. Suppose we have a manufacturer, an AM, could be the additive manufacturing machine. So this is printing their prints parts, right? And we assume this machine will produce the same parts for maybe 100 of them or many of them. Now, we assume the dimensionality accuracy, mean dimensionality accuracy. The mean is about the population, okay? The population is about 100 millimeter. And the standard deviation sigma is about 10 millimeter. Okay, now let's assume we are doing the manufacturing of the same parts, okay? And then for the same dimensionality, this part is a cube, and with 100 millimeters in all the 3 dimensions, and with standard deviation of 10 millimeter. Okay. Now, if we take (25) parts, what is the probability that the average dimension, nanity, accuracy will be less than 95 millimeter? Okay, so the specifications, the machine can do about mean 100 millimeter, standard deviation 10 millimeter. Now this is assume we have population, right? So the population is normally distributed with mu and the sigma square. That is approximately normally distributed with 100 and the 10 square. Now, what is the X-bar distribution? That will be mu sigma square over n. So this will equals to normally distributed still 100, but this will be the 10 square over 25. Okay, so this is normally distributed with 100. So variance gets smaller. So it's about 2 square. So it's 4. 100 divided by 25 is 4. Now we want to see the probability, the average dimensionality of these 25 parts, right? Okay. So that is the probability. What is the probability? X bar less than 95. So we know that if we have already know the distribution of X bar, right? So what we want to know is what is the probability of X bar less than 95. So this will become, if we do the normalization. Why do we do the normalization? Because most of the statistics will give you, the books will give you the standard normal distribution table to check the probability. But if you have a computer or the Excel, you can just get this probability based on this distribution. This will be X bar minus mu divided by sigma over square root of n less than 95 minus mu divided by sigma over square root of n. This equals to probability. This will become z, right? This is a standardization. Less than 95, we know the mu is 100. Sigma over square root of n is about sigma 10 over square root of 25. So this will become probability z less than minus 2.5. So this will equals to 0.0062. Okay. So from this example, we know the population standard deviation, and we want to get the average, the distribution of the sample mean. And then for 25 parts, we want to see how it will be less than 95 millimeters. This is how we leverage the central limit theorem to solve the problem. Okay, so this is the end of the central limit theorem.